Right, thanks a lot. So over the next half hour or so, I'm going to talk to you about, yes, precisely this, probabilistic programming with Gaussian processes, and the work I've been doing on that in Julia. So this is kind of joint work with, between myself and Wessel and my supervisor, Rich Turner, at Machine Learning Group at the University of Cambridge. And the slides, if you want them, are here. I just uploaded them a second ago. Right, so GPs. Why bother? Why should you care? So kind of the usual description is they're kind of flexible, interpretable, uncertainty-aware, probabilistic models for functions. We'll get into kind of more concrete description of that shortly. And the interesting thing is that you can take simple GPs and combine them to make more complicated ones and to express more complicated beliefs about the world. As with all Bayesian models, there's a kind of natural data-efficient way of doing inference in hyperparameters. And so they're quite unique in the fact that exact Bayesian inference is tractable for kind of small to medium-sized models. And by that, I mean small to medium-sized in terms of the number of observations you're working with. And there's a whole class of either very, very good or excellent approximations in the large data setting. And it starts to get quite complicated, and there's lots of things you can do, but there are lots of different, there's a whole literature on this, which I won't go into in this talk, but there's more on that in the GPML textbook, and so that's why I think you should be interested in GPs. So now I'll just kind of introduce you to what a Gaussian process is by way of multivariate normal distributions. So this is a presentation of these that I've seen a couple of times, and is my kind of preferred way to introduce them. So we're going to start by visualizing samples from a multivariate Gaussian in a slightly strange way. We're going to associate, so we've just got a one-dimensional multivariate Gaussian to start with. I've drawn 5 samples, and I've associated them with 0 on the x-axis and plotted the sample value on the y-axis. And these have a variance of 1, hence the matrix 1. And now we're going to consider a 2-dimensional Gaussian. And again, draw 5 samples, and the second sample is going to be associated with the value 1 on the x-axis. So the second dimension of the sample is going to be associated with the value 1 on the x-axis. And for each of the 5 samples, I've tied the first and second dimensions by a line. And there's some positive correlation between these two things. Again, this covariance matrix here. So still kind of low-dimensional Gaussian, just a slightly strange way of visualizing it. And we can kind of rinse and repeat and add a third dimension, do the same thing. And the thing that is important here is that we're going to have the covariance between dimensions that are closer in the x-axis be more. So the first dimension is more correlated with the second dimension, and the second dimension more correlated with the third. First and third are less correlated with each other. And so we can kind of carry on playing this game, and I'll drop the covariance matrix now, but carrying on with this idea of things that are closer in X are more highly correlated. And so we've still got 5 samples from multivariate Gaussian here, and we're just going to continue to do this and add more dimensions. And so now we have 5 samples from an 11-dimensional Gaussian that maybe start to look like samples from something that looks vaguely like a function, hopefully. And so we can take this another one step further and then start kind of filling in the gaps between these dimensions, adding more dimensions, again sticking with the idea that if you're closer in X, you're more highly correlated. And so add points. Oh, here I've just changed some plotting. Now we'll add some points in between, and then we'll continue to do this. And as you see, I wind up with more highly correlated Gaussians, and so we've kind of wound up in this situation where we have these smooth function-like things. And we've done this by just sampling from multivariate normals with a particular covariance structure. And we've parameterized that covariance structure in terms of the x-axis. And so you can take this to its kind of fairly obvious limit and start kind of associating a random variable with every element of the x-axis. And so now we're going to have a mean function that tells us what the mean is everywhere. I mean, it's been 0 here, but and a covariance function that tells us between any 2 pair of points on the x-axis, how much do samples from those points covary. And this is what takes us from a multivariate Gaussian to a Gaussian process. So just to make the analogy between the two kind of concrete from a mathematical perspective, so we've got a multivariate Gaussian on the left, F, with some mean vector mu and covariance matrix sigma, both d-dimensional. And then on the right, we've got the kind of analogous Gaussian process, which has a mean function M, covariance function C, and so the function maps from, in this case, the reals, and the covariance function maps from pairs of reals. Before going on, I'll just say that it's not restricted to the reals, but we'll stick with the reals for the sake of simplicity. The inputs here being the reals, but we'll stick with the reals for the sake of this talk. So there's the thing that makes Gaussian processes work. So obviously, at this point, we've got this kind of infinite dimensional Gaussian thing called a Gaussian process, and you can't deal with that on a computer. So the thing that makes them work is the fact that it's this marginalization property of Gaussians, which just says that if I'm only interested in a subset of Gaussian random variables, I can just ignore all the other ones. So I can ignore an infinitely large number of Gaussian random variables, just consider the kind of finite subset that I'm interested in. Say, if I have some observations at some input locations, call those input locations X, and I'm just interested in the random variables F at the locations F, X, so that's this notation here, F brackets X, so the vectorized F of X, if you like. That will be normally distributed, so it's just a finite dimensional normal distribution again, with some mean vector M and some covariance matrix C, which is given by the mean function and covariance function. So the point here is that we've got rid of all this kind of infinite stuff, and we can just work in finite dimensions, and if we want to make predictions at some points, we can do that, conditioned on having some observations at some points, and that also drops out from some kind of textbook Gaussian properties. So I won't go over this in too much depth, but if you have, so here we're finite dimensional Gaussian again, if you've got a kind of a block vector F and G, and you want to condition on observations of F, then you get a new multivariate normal, which is the thing on the second line, with some new mean sigma prime and some new covariance sigma prime. Doesn't really matter what these are, but they're simple expressions. And you can do an analogous thing for Gaussian processes. So you take your prior Gaussian process F, and you condition on the value of F at some locations X, and then you get a new Gaussian process with some new mean function and new covariance function. And so what this lets us do is kind of nonlinear regression. So I'm just going to walk through a basic example to make things concrete, and then we'll get on with some more interesting stuff. So here I've just visualized a sample from a GP with mean 0 and this covariance function here, which is a very standard covariance function you'll see all over the place. And what we're going to do is assume that we're just going to get some observations of it that we want to condition on, so these 3 points. And we're not going to actually get to see the rest of the function, we're just going to see it at these 3 points. And then if we compute the posterior GP and take samples from it, you get this kind of thing, where the samples from the posterior GP, they go through the observed points, because that's things we've observed, and they deviate from that elsewhere. And then we can look at and so this gives you some notion of your uncertainty about the function away from these points. And so this is where the uncertainty calibration comes in. And the common thing to do is to plot the mean of these and the plus or minus 3 standard deviations. So you've got some kind of idea of the mean of the distribution over the posterior distribution over functions and your uncertainty about the function at any point given these observations. So, sorry, more stuff. Combining GPs. I will get to some Julia stuff in a second, I promise. There are lots of common things you can do to combine GPs, specifically any affine transformation, if you can actually compute it. So if you take an affine transformation of a GP, you get a new GP, and the properties of the new GP are determined in terms of the original GP and the affine transformation you have. And so there's various things you can do there. It's kind of limited because they're kind of linear-like transformations. And so here's an example here, which I've done using the Stheno package, which is if you have, so I've got an additive model here. So taking the first example from here, F3 is F1 plus F2 on the addition line. So I've got some prior over F1, prior over F2, and I've just said that F3 is the sum of those two things everywhere. And what Stheno will let you do is make some observations of whichever ones of these you like. Here I've chosen to make observations of F1 and F3. And then it will let you query your posterior belief over these things. So, for example, here are some, in the vein of the previous example, given that I've observed some values of F1 and F3, I now have, I have less uncertainty about the values of F3. And this takes into account both observations of F1 and F3 together. And similarly for F1, and you'll notice here where you have both observations of, if you've got kind of bits of F1 where you've got observations of F3, the blue one, so, and you don't have observations of F1, you'll have kind of lower uncertainty, but not zero uncertainty. But where you've got no observations of either, you've got high uncertainty, and this is a consequence of the fact that we know that F1 and F3 are related in a particular way. And so Stheno will just do this for you. And similarly, we didn't make any observations of F2 whatsoever, but we know some stuff about it by virtue of the fact we know stuff about F1 and F3. So this leads us to kind of what Stheno is. It's a thing for constructing these objects that I call the Gaussian process probabilistic program, or Gaussian process probabilistic programs. And they're kind of a collection of these independent atomic GPs where, like the first thing we specified, where we have a mean and we have a kernel, and ways of combining those things to make more interesting things, and then doing inference on those. A GPPP is a GP in some sense. I'm not going to go into it, but it's kind of nice. And interestingly, so conditioning is an affine transformation. So you can have, so inference is like part of the kind of the forward model, as opposed to, if you take like Turing, you kind of write your forward model, and then you say do inference, and it just kind of does inference. Here you write your model, and then you write some other statements which are part of your model that say, okay, I'm going to have the posterior of this GP. So an example kind of program, so the maths on the left and the code on the right. So here we've got two atomic GPs, F1 and F2, where I've specified the mean and covariance. And F3 here is some affine transform A3 of F1 and F2, which here is just add them together. And F4 is another affine transform, and here I've just said, it could be anything, but I've said it's going to be the conditioning affine transform. So F4 is the posterior distribution of F1, given that I made some observations of F3. So what can a GP probabilistic program do for you kind of at a very high level? Given that you've written your program down, you can kind of sample from any bits of it. You can compute the log marginal likelihood, the log PDF of any observations of any of the component processes at the same time. You can compute the posterior of any of the component processes, and for kind of those who are into the GP literature, it kind of gives you a way to kind of specify fairly non-standard multi-output GPs, which isn't something you can normally do in other frameworks. And all of these things, existing GP frameworks in other languages or in Julia already, you can do bits of, but this is kind of a more general version of most of those things. And the way I like to think about it is the usual probabilistic programming thing of, well, you could have done it all by hand, but if you know what you're doing, but we can automate it, so might as well. Yeah, so Stheno.jl and Stheno, we have a Python version that Wessel maintains, are two kind of concrete implementations of this Gaussian process probabilistic program idea, and they just provide a collection of mean and covariance functions, a bunch of transformations, and the framework to glue things together, and things to do like sample, so kind of the usual kind of distributions style rand here. So we've got rand of some random number generator, and then we're saying sample from F1 at some locations x1, f2, at some locations x2, and give me n samples. And similarly, compute the log PDF of f1 at x1 being y1, f2 at x2 being y2, and conditioning, which we've already discussed. And the point of this is that these are kind of the basic primitive primitive operations you need and things that you need to be able to compute to work with Gaussian processes. If you can do these things, you can do everything else. This is fairly low level, but if you want to build kind of tools around them and stuff like that, these are the basic things you need, and then you can build up infrastructure quite quickly. So I'm going to go into some examples now. So firstly, zygote and Stheno. So I had a poster here last year on Stheno that was kind of, at that point the package was much less mature than it is now. At that point we couldn't propagate gradient information through it, which was very, very sad. But now zygote does work through it, which is great. So we can do reverse mode AD. And the thing that I omitted here, that people who know GPs will know, that these affine transformations will almost always have uncertain parameters. So if you're scaling a GP by some amount, how much are you scaling it by? If you're warping the input to a GP, I kind of changing the length scale of the GP, changing how quickly it varies, how quickly or how slowly should it vary. Those kinds of properties are governed by just hyperparameters. And so you need a way of tuning those hyperparameters. And the usual way with GPs is because we can compute this marginal likelihood, so this kind of f at x business, we can just optimize with gradient-based optimization. And so the gist is going to be write down a function to compute your log PDF that is a function of some hyperparameters, use zygote to compute gradients, plug into your favorite optimization tool. Jobs are good. So just example code here. I've got some model that's got some parameters theta, which spits out f1, f2, and f3. So this could be the additive model we had before. It is going to be very similar to that. And then we're going to look at the marginal distributions of f1 and f3 at locations x1 and x3, and these kind of the second argument of f1 of x1 and the second argument is just kind of the observation noise. So it's just how much uncertainty you have about the observations, and that's parameterized again. And yeah, then we just plug them into the log PDF with a particular, slightly different syntax to the one I had 2 slides ago. It's just an alternative syntax. You could have done the other two argument form. And this is a function you can just plug into Optim or whatever, and you're grand. You can just run this, minimize the negative log marginal likelihood as a function of theta. And I did this in a few minutes last night with a similar additive example where we're adding f1 to f2, and then I shifted things around so it would plot nicely, just move things up and down the y-axis. I had some observations of f3 and f1, but this time I made f2, I kind of assumed that f2 was more quickly varying and f1 was more slowly varying, and you just literally use that function you had before, and it found appropriate hyperparameters to fit the data, and this is the posterior distribution. This kind of marginal likelihood stuff is the textbook stuff that if you go and read Rasmussen and Williams, you'll find in there. But the interesting thing here that Stheno can do that other things can't do is it lets you conditional observations of, for example, f1. Normally you'd be stuck with just f3. So at this point I've just basically said you've got gradient information with respect to hyperparameters of models. So you can just go and manually do Bayesian inference if you like. You can take your favorite HMC scheme, plug it in, use zygote to get gradients, and again, you're grand. I've not got an example of this, but you could obviously do it. So Flux and Stheno. So there's an increasing amount of stuff in the GP literature looking at how do you combine GPs and neural networks, because we all like deep learning. And so I concocted a fairly kind of small example here. So it's a kind of sawtooth-like modulated noisy sawtooth thing. So the black dots are going to be training data, and we've got this kind of sawtooth-like function, and then I've cheated slightly and used GPs to modulate it. but the observations are kind of generated by squishing and expanding the sawtooth at various points in time and adding a bit of noise. And if you try and fit this with just like so here I've got an autoregressive neural network where I just have a function phi that has some parameters that's a neural network that takes the last few observations and tries to predict the next observation. And you just do that forward in time. It'll recover this black line here, which is it's not really done very well. It's just a regular old sawtooth. But if you go and do something slightly more complicated, and so you can almost ignore the first two lines of this. I'll come back to them in a second. I've taken this, so phi here is the neural network, and it's got some parameters and some data, and I've wrapped it in a thing that Stheno needs you to wrap it in, but don't worry too much about that. And then I've multiplied it by W. W is a GP that modulates the scale of the sawtooth. And then I've added on a bias term here, which is another GP, which is a bias varying through time. And this gives us our distribution F over sawteeth, I suppose. And yeah, you run some optimization scheme on this. And so again, the first half is training data, the second half test data. And it does something kind of sensible. So it learns that the neural network bit learns a kind of squished sawtooth that doesn't have the right amplitude. And then it learns to make a really, really large GP here that scales up so W here, so the blue thing here is W, and it learns to scale up the GP, the neural network. So again, so we get these kind of sensible-looking-ish things, and if you squint at the test bit, the uncertainty is fairly well calibrated, except for at the start here. But you know, you could. I'm sure someone could do a better job of this than I did. And so this obviously is a toy example, but there's some references here for actually interesting things to do with GPs and neural networks. So Turing and Stheno. So obviously the gist here is that you take your Gaussian process and you use it as a distribution inside Turing. And you would maybe use HMC to perform inference. There's other things you could do, but you know. So I've got a kind of Poisson regression-like example here. So this is a Turing model here. And so I'll just quickly step through the lines. So F equals GP, EQ, Turing GPC. This thing, ignore the Turing GPC thing. It's some unfortunate syntax that I hope to be rid of soon. But here it's just setting up a GP with a particular kernel. And then fx tilde f at x, 1 to the minus 9, is just saying that fx is a multivariate normal. It's multivariate normal distributed by indexing into the process f and adding a tiny, tiny bit of noise for numerical stability. And then we're going to make a bunch of IRD observations, independent observations, conditionally independent observations given fx. So here it's saying that the exponential of fx is going to govern the rate of a bunch of independent Poisson distributions, and then this product thing is a distributions.jl thing to just smush them all together into a vector. And so if you do this, so if you sample from the prior here, you get all these x crosses, which are just samples from Poissons with different rates. And if you look where the GP is, where the dashed blue line is a bit higher, you tend to get higher values of x because the Poisson rate's higher. And then if you run HMC, you get the solid blue lines in the solid region here, and it's done a reasonable job. It's not clear whether you should actually be able to recover the dashed blue line here. I'm not sure if the model is really identifiable, but that's I'm not going to worry about that too much for now. The unfortunate take-home point of this thing is that it's very much a work in progress, the integration with Turing and Stheno. There's a load of things that we know how to do, just don't quite work yet. So if you want to work with us, that'd be great. So to conclude, Gaussian processes are great, is what the first line says. The Gaussian process probabilistic program lets you do things with GPs that were previously doable if you knew what you were doing, but kind of tricky. And they can, in principle, be plugged into more general non-Gaussian distributions. And any of our wonderful probabilistic programming languages in Julia, they could hopefully be made to work with. And yeah, so Stheno is a concrete implementation of the GPPP kind of mathematical object in Julia. So there's a bunch of things I need to do. Hopefully with some collaboration at some point. Loads of documentation, GPU support. I don't think that should be too hard. The GPU ecosystem's looking pretty good now. Better integration with Turing. Hopefully I'll get some help there. Plotting, I suppressed all the plotting code here. It's currently really ugly just because I don't know how to write plot recipes. So if anyone wants to do that, that'd be wonderful. There's a standard inference approximation algorithm. There's a stochastic variation inference thing, which is fairly easy to do. Also, MLJ integration. Similarly with Turing, it's not quite clear how to integrate all of the features of Stheno in MLJ, but we should at least be able to give a nice user-friendly subset that's nicely wrapped. And then once users have found out how wonderful Gaussian processes are, they can come and actually check out Stheno. The serious things I need to do is improve the bus factor. I've already been doing this by myself. And there's some serious scaling things with kind of state space methods for low-dimensional GPs, and also some optimizations for vector-valued and matrix-valued GPs. So thanks to Wessel and my supervisor Rich, and to Hong and the Turing team, and Invenia Labs for continued support. And yeah, some links, and there's also some references. Thanks.
Hey, really cool work. Thank you. So either in the current Turing integration or a planned future Turing integration, if you sample from F at some X's, and then later you sample at F from some other X's, is that conditioning on the previous sample?
That would definitely be the intention. Yeah, that's a thing we know how to do in principle. I have an implementation that doesn't quite work. But yeah, that's definitely the intention. And also, if you have a more complicated set of GPs, everything should just be consistent. So that's where we're going.